Hello, this is Chapter 14, Assignment Problem 13. The particular question asked related to Part D, but I'm going to go through the entire problem to demonstrate how the facility of the textbook author wanted this problem solved. So what's important is that you watch this particular video where it gives you a problem walkthrough. And this walks you through step by step what I would consider to be a brute force method of solving this problem, but it does work. Those of you who may have used the data analysis tool and the regression function in the data analysis tool will see that you got output from the summary output of the regression analysis. By that I mean if you transferred the data for X and Y into Excel and then use the data analysis tool, assuming you have it loaded in your upper ribbon of Excel, you click on regression. I define the X values. I'm sorry, those are the Y values. I always get that backwards. And the X values, along with checking labels. The confidence level is not critical for this particular problem, but I use 95. I define the output range to start in D2, which is where the output begins. And I also checked for the residuals. Now, I didn't originally ask for a normal probability plot, but I did ask for the residual plot. And having done that, I'm going to cancel this because I've already done the output. This is the output that you receive. And this will satisfy all of the problems, all of the parts of problem 13, except for the standard residuals. If you enter in these standard residuals, they'll be marked wrong. And I'll show you why that is in just a moment. But this is the y-intercept. This is the slope of the x variable, the sum of squares regression, sum of squares errors, and the total sum of squares. In the residual output area, these residual values will also be considered correct. The problem is the author didn't want you to use Excel built-in functions to calculate the standard residuals. They have a different method that they want you to use. You might want to pause this video to jot down these numbers. And as you can see, entering in those values from the regression output will be correct in all instances. The scatter diagram that matches our residual plot is diagram 3, which suggests that the error term assumptions are not satisfied. You'll need to check section 14.8 of the textbook for those assumptions. What's key, however, is this standardized residual computation. If you use the values from the Excel built-in function of the regression analysis, those will not be correct. These numbers can only be obtained if you use the step-by-step method outlined in the video. And this is the method that they outline in the video. It is quite long and tedious, which is why I'm sure some of you may have avoided it. To be honest, I wanted to avoid it, but you can't avoid it if you want to find the answers that they have in this exercise. We start with our x and y. We take the sum of those. We calculate the average for x and y. And then these steps, D, E, F, G, and H, are in chapter 14.2. So we calculate the difference between each x value and the average of the x values, x bar, the y values, and y bar. We take the sum of those two deviations, take the product of those two deviations, and sum those. And then we take the square of the x minus x bar, and we sum those as well. And for the equation for B1, which is the slope, it's the ratio of that sum of the products of the deviations divided by the sum of the deviation squared of the x minus x bar. That gives you B1. Likewise, B sub 0 is the average of the y values minus B1 times the average of the x values. That is your y-intercept. Same values we got using the Excel built-in function. But these steps then are needed to compute the residuals and to get to the standard residual. So we start with y hat, which is simply the predicted values using the x values. So we use our regression equation to calculate the predicted values in each case for each x value. I'll let you see the equations again. Yours may be slightly different when you lay it out this way, but you're taking the y-intercept and you're adding the slope times the corresponding x value. Again, these equations are in your book, and it's also in that video. Next, you calculate the error, which is the difference between the actual y value and the predicted y value. Next, you square that error number, and you take the sum. And this is literally the sum of squared errors. Next, you take the actual y value and subtract the average of the y values. You square that deviation, and you take the sum of those square deviations, and that is your sum of square total. And they remind you that the sum of square total is equal to the sum of square residuals plus the sum of square error. So we use this to solve for the sum of square error. Simply by subtracting the sum of square error from the sum of square total, and that gives you the sum of square error. We then use this number to calculate the coefficient of determination, r squared. which is the ratio of the sum of squared residual divided by the sum of squared total. And then we calculate S squared, and I should have placed, not that it matters in this case, but just to get in the habit, it's a good idea to anchor your count, your array using the count built-in function if the number of data points, or n, might be used in other places. So this is our sum of square error, and this, taking the square root of that, then gives us S. This is the sample standard deviation. That's important because that's going to be used later in our calculations. So now we're calculating H sub I, and this is in section 14.8 of your textbook, and it's also, again, referred to in the video. But this is a key step. This is a special factor. That's the best we can call it right now. That's used in the calculation of the standard residuals. These H sub I values are very important. And you can see the elements. It's 1 over n plus the x minus x bar squared divided by the sum of the x minus x bar squares. We then calculate the standard deviation of the ith residual, and this is where this h value comes in. In each case, it is s times the square root of 1 minus that h value. And you do that for each residual. And then the standardized residual is the error y minus y hat divided by that standard deviation of the ith residual. And that gives you your standardized residuals. And make a note of these numbers, because these are the correct numbers that you have to enter in order to have this part D marked correct. The last thing they ask you to do then is to select the proper standardized residual plot. I did that by simply bringing down the x values, bringing down the corresponding standardized residual values, and then doing a scatter plot of those values. And because this is curvilinear, the conclusion that you draw is the relationship of these values is not really linear, and therefore the assumptions of the error term have not been satisfied. So the linear relationship that comes from this standardized linear regression is probably not the best, even though our R squared is quite high. So that simply says just because you have a large R squared, it's not necessarily the best fit for the data. And of course, if you plot that data, you'll probably see that it doesn't really have the best possible linear relationship. So the error term may not be satisfied. Again, even though our R squared, the coefficient of determination, is 0.81, which would lead you to believe that the equation accounts for 81% of the variation of y given x, which is why the residual analysis is important.